What's up, guys? What I want to do in this video is to solve the problem 33 of the book of Halliday. It's the edition 10 and it's the volume 3, which is the volume about electromagnetism. This is a problem about a spire, and above that spire there is a path of current, actually a wire. And the thing happening here is that the spire has one side which it can vary in position, and because of the wire which has a current passing through it, a magnetic field it's being generated by the wire, and the magnetic field produces a variation of the magnetic flux across the spire, because the area of the spire itself is increasing. So the one thing that we have to determine, at least in letter A, is what's the magnitude of the electromotive force generated in that spire. And for that, the right equation to use is actually the definition, or not actually the definition, but is the form of the electromotive force, which equals the negative of the derivative of the magnetic flux with respect to the time. So the one thing that we have to determine is the magnetic flux, and we know that flux in general has this is calculated by an integral of this form, vector product of B dA, and this field B is the field generated by the current passing through the wire. So it can be calculated easily by the Ampere's law. So actually the B field generated by a linear wire of current equals, and I'll put a vector here, the magnetic permeability times the current passing through the wire divided by 2 pi, the radial distance from the wire, and is in the radial direction. So this is the expression for the magnetic field. And actually we have to calculate the magnetic field in the plane, or in a better way to speak, out of the plane of the spire, because the magnetic field is getting actually I think it's getting into the spire. No, sorry, it's getting out of the paper, or getting out of your screen. So at least in the position of the spire. So and I will draw two axes here, at least in two dimensions. This is y, this is x, and the position x equals 0, which is the position of the plane of the spire, we have a B field in the direction of x getting out of the paper or your screen, 2 pi, and this is the direction y, because this is not because x is 0. So we are in conditions to calculate the magnetic flux across that spire. So we get, and we are going to take all these quantities out of the integral sign, 2 pi. You observe that the element of area is in the same direction as the B field. So alright, x, they're in the same direction, there's y here, and this element of area, I'll write it this way. This is actually equal, if you take a strip or a rainbow, and that strip, this is the position x, of one dimension of the spire, and this is the y. So the element of area is the product of these two things. So I'll put right over here, this is x, and I will put xt because the position of the bar depends on the time, and the dy in here. So we get a magnetic flux 2 pi xt, and this integral should be evaluated from minus a plus what's the other dimension, L, or you can put a minus sign here once there is no difference, and the integral of dy divided by I equals the logarithm, and here we get a plus L divided by a. And now we can substitute these numbers, so we get a magnetic flux. Whoa, this sounds very cool. 4 pi 10 to the negative 7. I forgot the units of the magnetic permeability. I think it's Henry per meter or times meter times amperes to the negative 1, because the current has the units of ampere. It's 100 ampere, but I'll not risk myself to write the units because I can make a mistake right now. So I'll multiply by 100, and actually we don't have the position of the bar, because the only thing we have is the velocity from which the bar is moving. So I think it's time to get the electromotive force by derivating this thing with respect to the time. And the only thing that depending on the time here is actually the x variable. So we get here is v, because dx dt equals the velocity divided by 2 pi, and we can do this logarithm right over here. A is, if I'm not wrong, is 10 millimeters, I think, and L is 10 centimeters. So I think we get 11 here, and we can substitute all of the other numbers. So 4 pi 10 to the negative 7, and I will not risk putting units in here. The velocity is 5. This logarithm, I don't know what's the exactly value, 2 pi, but I know the answer, and the answer is actually, let me see, 240 10 to the negative 4 volts. So this is the electromotive force generated by the wire, by the magnetic flux variation induced by the current in the wire. So now it's time to go to letter B, and I'll pause and clean this page. So now that I have cleaned the page, we're going to solve the letter B. And the letter B, I think it's the easiest letter in this problem, because you have the resistance, you have the voltage on the circuit, even it doesn't seem to be a circuit, and the problem asks you to determine what's the current passing through the bar, the spiral. And you may use this equation right over here. Actually, it's the Ohm's law, and the dates I think you have. This is the voltage, And probably you guys don't think this is exactly the voltage in the sense of the traditional voltage due to an electric field. And in part, I think you guys are correct, because if you're going from one point to another, you should get zero differential potential. In this spire, you have an electromotive force, which means that there is differential potentials in points of this bar. But you have to remember that the traditional the traditional voltage or differential potential has an origin in the electric field. This is the definition of the electric potential. And when you calculate this integral in a closed path, you get zero differential potential because you're getting out from one point and you're ending the same point. And this seems to not happen with the electromotive force, but you guys have to remember that the electromotive force has another nature. This is generated by magnetic flux variation, and it's interesting to note that the integral of B dl is different from zero, and this electric field is actually a conservative field. Is actually it's not necessary to write this. It's a conservative field, and B seems to be not. But anyway, I'm telling too much bullshit right now. This is not necessary. So the one thing we can calculate is put these numbers here, volts divided by the resistance is actually, the whole resistance is actually this, and you get a current of approximately 6 to 10 to the negative 4 I think it's ampere. And now it's time to move on to the letter C. So the letter C asks you to calculate the power supplied or maybe generated by the current in some sense in the circuits. So you may remember the definition of the power in this case, in the electrical case. So you only have to multiply the voltage, which is the same thing as the electromotive force in this case, times the current. And the voltage, you know that is the resistance times the current. And there is also a current here, and you get current squared. So the power equals, actually this is a dissipated power. This is on, this gets 36, 10 to the negative 8, and the unit here is ampere square times ohm, and you get a power of 144 10 to the negative 7 watts. So this is the answer to letter C. And now we move on to the letter D. Now moving on to the letter D, it asks you to determine what's the magnetic force acting on the side of the bar, on the side of the spiral, which is the bar. And maybe you guys think that well, there is no magnetic force acting on it since the bar is moving with a constant velocity, and if there is no acceleration, so there should not be a force. And I would agree with you if, except for the fact that there is acceleration, there should be acceleration, because this bar is formed by charges and other particles actually, but uncharged particles. But the force, you have to remember that When you put a charge in a magnetic field and if this charge is moving, then a force acts on this charge. And now we have actually a set of charges, which is the bar itself. And you have the wire, which has a current passing through it, which generates a magnetic field. And a magnetic field acting on the charged particles of the bar exerts a forces on the bar. I'm not sure if I used the right word, but anyway, I think you guys understand that. So the one thing that we have to do is integrate all of the forces acting on all of the charges. Actually, the forces acting on all of the charges. And we have to remember that a force acting in one charge equals, in this way, when there is a magnetic field acting on a charge with velocity v. And when you integrate this thing, you should integrate in the Q. And we can also, actually, we should take a change of variable, change from dq to dt, the time. And this is an induced current because we forget the wire for a little bit, and this is the current passing through the spire. And the definition of current is dq dt, so we can use this expression. And you can change the variables again, this time in length. I think it gets like something like this. This is length, I'll call it x because it's in the horizontal dimension, direction, or it's actually the vertical direction, sorry. And here we have the velocity, because length divided by velocity equals time. And we can change the variables like that, so we get the total force acting equals, and we have to consider the right direction of the particles. The particles which is perpendicular to the magnetic field because of this vector product in here. So we get E, actually I, the current induced, divided by V, the magnetic field. I'll write that here is the current, this is the current generated, or the current of the wire, the magnetic permeability, 2 pi, and dy, and there's a vector y in here. And also again we calculate from -a to -a plus L, because we integrate all of the bar which contain the particles, charged particles, perpendicular to the magnetic field. So the total force equals, I think we can change the variables now. No, it's better to do that later. Sorry, to substitute the variables. 2 pi, and we got the logarithm term in here, divided by a. And I have to see if this is correct, if I forgot something. I think it's correct. So the only thing we have to do is substitute. I hope there is space in here. There is 100 current ampere. 6, I'll not put the units. The magnetic permeability is 4 pi times 10 to the -7 divided by 2 pi. We get to 10 to the -7, and this unit is Newton. And this equals, I have to put down here, 2.87 10 to the -8 Newton. So if I'm not mistaken, this is the right answer of this problem. And finally we go to the last letter A. And in this letter it's similar to the letter, I think the letter C, the letter about the power supplied. But anyway, this power is calculated consider that the force acting on the bar and the velocity of the bar, because it's like you should stop the bar from moving. So and I think you guys know that the power equals the force times the velocity. And one approach to see this is actually consider the power, the definition of power, which is dw dt, but dw is actually the force dx, consider the horizontal direction, dt, and if the force doesn't depend on time, you have dx dt in here, and this is the velocity. So the only thing you have to do is change the verb, is substitute the quantities. So the force equals this thing, and the velocity equals this another thing, and you get a power of 1 times 44 10 to the negative 7 watts. So this should be the right answer for letter A. So guys, I hope you have enjoyed this video. This is a huge problem with 5 letters, and I hope you have a good day, and I think I see you guys in the next problem. So bye bye.